Good morning and welcome to Tech 293 for Tuesday, January 26th. Today I'm going to make two videos. In this first video, we're going to wrap up the materials science section of this class. And we'll do that by talking about 5 different categories or types of materials. And we'll talk about the behavior of those 5 different categories or types of materials by relating it to the materials science that we've already talked about in the past week or so. So we'll talk about the types of bonding that are inside the materials and the types of lattice structures and the types of grains that might be inside those materials, which are going to give them their mechanical properties. In the next class session on Thursday, we'll start talking about mechanical properties of materials and how to test those mechanical properties. And we'll start by talking about hardness testing on Thursday. All right, that's going to be the first video for today. In the second video for today, I'm going to do Lab 2, and you'll watch me do Lab 2 and pretend like you're my lab partner here with me. I'll probably do it just right here in my office. And so as you watch that video, you should have your Lab 2 instructions out in your lab manual, and you should follow along with the instructions. And you should also have something to record the data, because I'm going to tell you what the data is, and then you should record that so that you can use that to do the analysis and write your lab report for Lab 2. The last thing I want to mention before we get into the first video material, here is the schedule. So let's take a quick look at the schedule. Today is January 26th, and we have Lab 1 due today. So it's due at 11:55 p.m., so make sure you submit your Lab 1 lab report by 11:55 p.m. tonight on Reginet under the Assignments tab. We're going to do Lab 2 today. That's the second video today, and Lab 2 is due on February 2nd. That's 1 week from today. So again, by 11:55 p.m. on February 2nd, make sure you submit your Lab 2 lab report on Reginet under the Assignments tab. All right, so with that, let's go ahead and switch to the slides and wrap up the materials science portion of this class. All right, the first couple slides here are more or less a recap of what we've talked about so far. So we've talked about bonds and their impact on mechanical properties of materials. We've talked about 4 types of bonds. 3 of those were atomic level bonds. 1 was intermolecular bonds. We've talked about influencing factors on the phases of matter. We've talked about lattice structures and their mechanical properties. And what that leaves us with is our 5 groups of engineering materials, which I mentioned a few days ago when we started talking about materials science, but I said we'd come back to it. And that's what we're coming back to today. 5 different groups of engineering materials and their mechanical properties. So those 5 groups of engineering materials, things that we build stuff with commonly, are metals and ceramics and polymers. Those I would say are really the basic fundamental 3. And then usually we add in these other 2. Wood, which is actually a natural polymer, but it's so common and frequently used in building stuff that we oftentimes put it in its own category. And then composites is kind of its own category because it's a mixture of other stuff. And so composites is probably the most diverse category because it represents a lot of different stuff, 2 or more things mixed together to get desirable mechanical properties. All right, we talked about 4 different types of bonds. And now we're going to get into these 5 different categories, all right? And we're not even going to get into a huge amount of detail on any of these. Later on in the class, we will. We will spend a whole day talking just about ferrous metals and what are they and how do you change their properties and stuff. And then later on, we'll spend a whole section of the class talking about heat treatment, which is also dealing with metals as well. But we'll talk more later in the class about ferrous metals and non-ferrous metals, but I'm kind of just introducing them today. So we're going to deal quite a bit in this class with metals and polymers, and there's a whole separate class, TEC 285, on polymers. So my intention is not to go in nearly as much detail as TEC 285 does on polymers, but we need to know a little bit about polymers in order to be working with them. So we are going to do tensile tests and compression tests and various other tests on polymers. So you need to know a little bit about how they're made and how they're held together and different types of structures with polymers. So if you've taken TEC 285, I'm sure that they cover this in 285, but you've got thermoplastic polymers and thermoset polymers, and then elastomers are kind of their own category as well. We'll talk more about that today. And then ceramics, we'll talk about it today, but we don't do a whole lot of testing on ceramics in this class. Same thing with composites. We'll talk about it today. We do a little bit of testing on composites. We'll do one in lab 4. We'll have a composite that we do some tensile testing on. It's kind of neat. We'll talk more about that today, and then we'll talk more about wood today. We do a lot of testing on wood in this class because it's really common and it's easy to procure, so why not? So we're going to do tensile tests and compression testing and shear testing and flexure testing on wood, in addition to a bunch of these other types of materials in this class. So let's get to it. So we'll talk about metals first. We can divide them into ferrous types of metal and non-ferrous types of metal. Ferrous metals in general means it contains iron. It has iron in it. If it's non-ferrous, it means it doesn't contain iron. That's generally the way that we categorize ferrous and non-ferrous. And if you can remember the periodic table and what the chemical symbol for iron is, it's Fe. And so that can help you remember. Ferrous starts with Fe. That means it contains iron. Non-ferrous, that means it doesn't have Fe, which is iron. So that's the best definition of ferrous versus non-ferrous. There are some other characteristics which are listed here. Usually ferrous metals are magnetic, although there are contrary examples that aren't. They're also usually prone to corrosion, although you can make, stainless steel is still a ferrous metal because stainless steel still contains mostly iron. But you can make some stainless steels that are pretty corrosion resistant. But in general, ferrous metals are more prone to corrosion than non-ferrous metals. And lots of times, almost always, I would say, actually, ferrous metals contain other elements. So you don't often use just plain old iron. Even cast iron is not just plain iron. There's other stuff added into it. And that's because plain old iron is not particularly strong. It's not particularly hard. It doesn't have great mechanical properties. So we add things to it and create alloys, which are a lot better to work with. So iron, plain old iron is a ferrous metal, but usually we add stuff to it and we make different kinds of steel. And there are thousands of different kinds of steel. And we'll talk about some of those later on in this class. Not this session, but this class. Non-ferrous metals, they don't contain iron. They're not usually magnetic. You can usually make them. You can make a magnet out of lots of different stuff. You can induce a magnetic field in lots of different materials, but they're not naturally magnetic. They're usually not as prone to corrosion, and basically any metal that you can find that doesn't contain iron, we'd call a non-ferrous metal. So metals are characterized by metallic bonding. That should be no surprise. And when you think of metallic bonding, you should think of this lattice structure. That's where all the atoms are. But then the valence electrons are just floating around in this sea of electrons, or a pool of electrons. So that's what you should think about when you think about the atomic structure of a metal. And all those valence electrons in the pool of electrons, they're all shared between all the atoms in the lattice structure. And because the electrons are not held tightly to the atoms, it allows for deformation, which allows for the material to be ductile, tends to be more ductile than, say, ceramics or something like that. So metals tend to be moderately ductile. It depends on the type of metal, but in general, they tend to be moderately ductile. And alloys, we've talked about this, but you can have interstitial alloys. like steel, which is just iron and carbon at its most basic level. Or you can have substitutional alloys, which would be bronze or brass, or Inconel are all substitutional alloys, where you take the lattice structure and the vertices of the lattice are now not all the same chemical element. So now you're taking some other element and substituting it in for the original base material in the lattice structure. Inconel, by the way, is a very corrosion resistant and also very strong material. It's expensive, but it's what's used in really high temperature, high corrosion environments. In my industry experience, we used Inconel for like steam piping and steam generator tubes and things like that would be exposed to really high temperatures and high potential for corrosion where you really didn't want them to corrode. You could use Inconel. And then we gave an example of where alloys can be both substitutional and interstitial, and that would be like some of these exotic steels, where you could have a substitutional element that substitutes into the iron lattice, and you could have interstitial elements, which would most likely be carbon, interstitial inside the lattice structure. We talked about lattice structures last time. We talked about 14 different types of Bravais lattices. And remember there was that song that I played for you. And I think I remembered after I made that video that I didn't specify when you need to make that YouTube video if you want to do the, not really extra credit, but if you want to memorize the lyrics and recite them in order to get 100% on your first exam. If you want to do that, then you can. That needs to be done before the first exam. So you can't take the exam and bomb it and then say, oh man, I need to memorize that song. So if you want to do that, then you need to do that before the first exam. So you need to post the video and send me the link to your video on YouTube of you reciting the song lyrics before exam 1, all right? If you want to take advantage of that. I don't know, honestly, I don't think I recommend memorizing that. I think you're better off just studying for the first exam. But hey, it's up to you. It's up to you. All right, so we talked about those already. Simple cubic and body-centered cubic and face-centered cubic and hexagonal close-packed are the 4 that I want you to know a fair amount of details about. And we also talked about grain structures last time and how it's important to know that any material, whether it's water or molten steel or any liquid that is freezing, it doesn't just instantly turn to solid at the freezing temperature. It takes time. It takes a finite amount of time for something to freeze, and when it freezes, it starts out by creating solid structures at the inception points, and then gradually the solid grows out from that, out from the inception points until they all meet together at these grain boundaries. And the grain boundaries are really important to the mechanical properties, and particularly the size of the grains are really important to the grain boundaries, because these lattice structures, say here and here and here, they're at just random orientations. They grow at just random orientations. So the dislocations that you might get along slippage planes have a really hard time, say, going from this grain into this grain, because the slippage planes are at different orientations. And so these grains and the grain structures have a really important role to play in determining the mechanical properties of materials. And that, we will talk more about that and more details about that in the heat treatment section of this class in a month or 2. Metals are really nice to work with because they tend to be rather ductile, and yet they're also pretty strong also. So they're really nice to work with. You can cast it, you can machine it, you can weld it, you can drill it, you can forge it, you can heat treat it. There's lots of different stuff you can do with metals. So they're pretty nice materials to work with. Now I'm going to give you kind of a series of line graphs or plots like this for each of the 5 different categories that we talk about today. I don't need you to memorize precisely, where these fall on each scale, but I want you to know in relative terms, like I think you should know, generally speaking, which are harder, ceramics or metals, or woods, So in relative terms, I want you to know where these materials fall on these different scales. All right, so metals tend to be moderately hard, moderately ductile. It really, there's a lot of variation built in here because there's a lot of different kinds of metals. But they generally tend to be moderately hard, moderately ductile, kind of medium heat resistance. And that's because those bonds are not particularly strong with the sea of electrons. And so it doesn't take quite so much thermal energy to break them apart compared to, say, a ceramic. All right. Corrosion resistance, it tends to be medium to poor, depending on whether we're talking about a ferrous metal and what kind of ferrous metal, or some kind of non-ferrous metal. And conductivity, they tend to be very conductive because of that sea of electrons, and those electrons can just move and conduct electricity. All right, ceramics are the next category that we're going to talk about. Generally speaking, ceramics are, well, they're kind of hard to define, first of all, because there's a large range of them. But generally, they are characterized by a metal and a non-metal. So one element from the left side of the periodic table and one element from the right side of the periodic table. And they're held together, could be with covalent bonds or ionic bonds. Oftentimes it's ionic bonds, but it could be covalent bonds as well. So you can see why they're a little bit difficult to define. A few common examples: tungsten carbide tends to be a really strong ceramic material. We tend to use that to make cutting surfaces. Like you might see that on a blade, like a circular saw blade or bandsaw blade or something. It tends to be very hard and very strong, and it can be sharpened, and it makes a good cutting material. Aluminum oxide also is pretty hard and strong. You're seeing a trend here probably. It also makes a pretty good cutting material. Usually this would be more for like sandpaper. You might put this on like sandpaper or something. Silicon dioxide is glass. Now notice here, silicon, this is kind of an exception to the rule about a metal and a non-metal. All right, oxygen is definitely a non-metal. Silicon is actually a metalloid or a semiconductor, so it's not really a true metal. That's why I had to give the caveat that it's usually a metal and a non-metal held together. So glass is considered a ceramic. Silicon is, in this case, kind of taking the role of a metal, but it's really a metalloid or a semiconductor. And then pretty much anything that would fall under the category of like clay or pottery or something like that, those are all considered ceramic materials. Usually they contain some combination of aluminum and silicon and oxygen. So clearly aluminum is a metal, oxygen is a non-metal. And a lot of times they have other stuff mixed in. So we can generally categorize ceramics into these three categories. One are the crystalline structures, and these actually do form crystalline lattice structures. So all of these form crystalline lattice structures. Glass does not have a crystalline lattice structure. In fact, you've probably heard it's an amorphous solid, which means that it can move over time, slowly, 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 but it can actually deform over time if you apply a stress to it over time. And then there's others. For example, cement and plaster are a good example. Cement is the stuff inside concrete that holds it all together. Cement and concrete are not the same thing, even though a lot of people use them interchangeably. Cement is considered a ceramic material, but concrete, we'll talk about later, concrete is a mixture of cement and rocks and sand and water. And so that's actually considered a composite material. Here's a bunch of ceramic parts. Most of the time, types of plates and dishes are often ceramic, at least nice ones. We don't, in my house, we don't give ceramic plates to our kids. They eat off of plastic plates and cups and stuff because they spill it all the time. There was actually, that reminds me, there was a couple weeks ago, we were keeping track. There was, I think it was 5 nights in a row, 5 dinners in a row that my 10-year-old kid spilled his drink at dinner time. 5 consecutive nights. And he wasn't trying. He really wasn't. He wasn't like, oh, this is a game. I'm going to spill my drink again. No, he's just that, I don't know. He's just that irresponsible, I guess. Or like, he's full of energy. So he's just always moving around. Anyway, I digress. Over here, these parts take advantage of the fact that ceramics have very low conductivity, and these are actually components that hold transmission lines together. And when you're suspending a transmission line from a support pole, you don't want the electricity to go through that pole into ground, right? So if you look at a transmission line, you'll see that it's actually held or suspended from the transmission line support pole by a big fat resistor that has a really high resistance because you don't want the electricity going to ground. So that's what this and this and this are. And then over here, this is a little bit more difficult to see, but I can tell you that it is a prosthetic that goes in your body, and these are a ceramic ball for a ball and socket. So these would be either for like a prosthetic hip or a prosthetic shoulder joint. And every time I look at this, I have to admit I wince a little bit because I have a history in my family of having bad hip joints. There's a lot of people in my family that have hip replacements. And I know that hip replacement surgery is pretty gruesome. I had I have a doctor friend, and he's told me anecdotally that yeah, when they do hip replacement surgeries afterwards, they oftentimes have to wipe down and clean the ceiling after these hip replacement surgeries. So I am not looking forward to that, and I don't want to think about that too much, but it's probably in my future, and I'm probably not helping myself by continuing to run. But I don't run long distances anymore. I did a marathon once, and never again. I don't think I'm ever going to do anything longer than a 10K ever again. I just don't feel a need to. So. Moving on, ceramics. So they do have strong bonds, and they oftentimes, not always, but often have lattice structures. And that makes them strong and hard and heat resistant and also very brittle. They can't just slide along slippage planes very easy because they have really strong bonds holding them together. They don't have freely moving electrons, and so that makes them resistant to transmission of heat and to electricity. And our table of properties for ceramics, they tend to be very hard. They tend to be not ductile at all. You know, when you take a ceramic plate and you drop it, it's not going to bend. It's going to shatter into 1,000 pieces. They tend to be very heat resistant. You're not going to be melting a ceramic. They tend to be very corrosion resistant. They don't rust or anything. And they tend to not be electrically conductive at all. Well, I shouldn't say at all. You know, I shouldn't use absolutes. They have very, very low conductivity. All right, let's do this one, and then we'll take a quick little stretch break. So polymers are the subject of TEC 285, so I don't feel a need to talk about these in great depth here. Generally, we divide them into either 2 or 3 categories. So if you divide them into 2 categories, then the 2 categories are thermoplastic and thermoset. Basically, what that means is that thermoplastic materials can be remelted. If you take a plastic part, if this was a thermoplastic, and I don't know what it is, but I don't think it's a thermoplastic material. But if it was a thermoplastic material, then I could melt this down, and then I could reform it into something else, or the same thing over and over and over again. And the reason that you can do that is because the long molecule chains, they don't form bonds between the chains. So all you have are relatively weak intermolecular bonds, van der Waals forces. You don't actually have covalent bonding between the chains of the polymer molecules. With thermoset, kind of the opposite. If this was a thermoset, and I think it probably is, then you would not be able to remelt it down. It just wouldn't work. It would burn, but it wouldn't remelt into a liquid material that you could then reform into something else. And the reason that it works like that, the reason you can't remelt it, is because those long polymer chains form covalent bonds in between them and hold those chains together. So you can't generally heat it up to break those covalent bonds between the chains of the molecules. So that's basically the strength of the bonds in between the molecules. The intermolecular bonds are what differentiate thermoplastic from thermoset materials. Sometimes we include this third category called elastomers over here. Elastomers can be either thermoplastic or thermoset materials, but generally they're just characterized by really weak intermolecular bonds, which makes them stretchy, really stretchy. So think like rubber. Like all of these kind of sort of have the characteristics of just really flexible and rubber materials, but they could be either thermoplastic or thermoset. And polymer in general, poly means many, and mer means a repeating unit, repeating over and over and over and over again. And that's what polymers are. Long chains of molecules. A molecule that is really, really long and repeated, and then the whole material is held together by the intermolecular forces, or van der Waals forces, between those long molecules. Polyethylene is one example. Here's ethylene, and if you have a bunch of ethylenes all bonded together in a long chain, then you have polyethylene. So here's an example, that's polyethylene, and you can have these really long molecules in some cases that contain thousands of individual atoms. Here's another example. Polymers, you can kind of think of them as like a bowl of spaghetti, you know, because they have these really long individual molecules. And so as you pull it apart, you know, as you take your, here's a couple of examples. I don't have an unstretched, or do I? Yeah, if I take one of these, so this is a polymer, and if you zoom in close enough, you would see that it's just kind of like long molecules that are kind of thrown together, kind of like a bowl of spaghetti. And then as you're pulling it apart, what you're doing is you're kind of untangling that bowl of spaghetti. And so you pull it apart and you get something that looks like this or like this, and you're just stretching it apart, and those intermolecular bonds are getting pulled apart. You're not necessarily breaking the intermolecular, you're not necessarily breaking the molecules, you're just pulling apart the molecules against each other. So the molecules are just sliding against each other. All right, and I said this before, thermoplastics can be remelted, and that's because they don't have bonds other than intermolecular van der Waals forces, which are relatively weak. they don't have strong bonds in between these long molecules, whereas thermosets do have these strong, these are covalent bonds between these long molecules. And so because they have these really strong bonds in here, you're not going to be able to remelt them. They'll burn, you can burn them, but you can't remelt them. So thermosets tend to be stronger and harder than thermoplastics. I'll say a few slides here. I'll say a few things about fabrication of plastics, although most of this I'm leaving to TEC 285 because that's a big part of what you do in TEC 285. So in general, you can mold them. So this is an injection molding machine. This is also an injection molding machine, kind of like the ones that we have down there in the plastics lab and in the classroom where we would be meeting, this class would be meeting. You have a hopper where the plastic pellets go in, and then you have an injection screw where it's also heating up the material and melting it. And then this screw is like an auger, and it spins and it pushes the material into the mold right here. The mold usually has water going through the mold to cool it down and to cool the plastic down and let it solidify. And then once you do that, and then once it's cooled down a little bit, then the mold opens, and then there are pins that come out. They're spring-loaded pins, and they push the part out of the mold, and then it comes down on the bottom of the machine. That's in a nutshell. That's more or less how it works. Vacuum molding is another important process, especially for thermosets. These tend to be used with thermoset materials. Basically what you do is you have a thin sheet of plastic material. You heat it up until it is soft. Again, you can't really melt it. It's not going to be a liquid, but you can heat it until it gets soft. And then what you do is you take that sheet of plastic and you bring it down on some solid object that you want to mold around. And then there are vacuum ports that suck the air out. And so what you end up doing is creating this nice mold, it's plastic mold on top of some solid surface. For example, if you had a pair of shoes, maybe you could make a vacuum mold of these shoes. So you put the shoes underneath, and then you take the plastic and you heat it up, and then you take the plastic film and you move it onto the shoes, and then the vacuum pulls the air out, so you're left with just this mold. And then once it cools down, then you can remove the plastic. All right, so polymers in general do not have lattice structures. They just have these long molecules that are held together with intermolecular forces, generally. There's no sea of electrons, so they're good insulators. If they're thermoplastic, then those molecules can slide past each other, which makes them fairly ductile. And with lower melting temperatures. But if they're thermoset, then they tend to have covalent bonds between those molecules, which does make them stronger, but it also makes them more brittle, less ductile. Brittle is the opposite of ductile, and also gives them higher melting temperatures if they will even melt. Some thermosets just won't even melt. So our scales of properties for polymers, they don't tend to be very hard. For ductility, we have to differentiate between thermoplastics and thermosets. So thermoplastics tend to be quite ductile. Thermosets, not. They're not very ductile because of that covalent bonding. Heat resistance, once again, we have to differentiate between these two. Thermoplastics, you can melt them, so they're not very heat resistant. Thermosets oftentimes can't be remelted, so they're more heat resistant. Corrosion resistance, well, they're plastics. They don't really corrode. So high corrosion resistance. And they're not very electrically conductive because they don't have the free electrons that can move around. All right, so, okay, we've done 3 of the 5 categories. I think I'll take a quick stretch break. So you can take a quick stretch break. All right. So what woods really are a natural polymer. All right. So they have long chains of material, and we'll talk about what those chains are called in just the next slide, I think. And we often talk about wood, but really wood is one of many natural polymers. Bone and leather and cotton and wool and tar and paper. Well, paper is made from wood, right? So all of these kind of have similar characteristics. They're all organic materials. They're all natural polymers. But wood is really what we focus in on because it's a key building material, whereas bone, not so much, not anymore. The main advantage of wood is cost. It's cheap. Even though we don't have as many, really, like forestry is getting more difficult and more expensive because there aren't the same number of forests that there were 50 years ago. But even so, wood is pretty cheap. And you'll see in a little bit that its mechanical properties are really not that great, but it's really cheap and it's easy to work with and it's available. And so those are the reasons why we tend to build a lot of things with wood. Fabrication is also really simple. We use subtractive manufacturing, which is just the opposite of additive manufacturing. Additive manufacturing is starting with nothing and then building stuff up, like 3D printing. Subtractive manufacturing is taking I have some blocks of wood over there, but if I take a block of wood and I cut it down to size, and then eventually I get to the right size, and we call that subtractive manufacturing. There's lots of different species of wood which have different properties. Oftentimes we lump them into either soft woods, like pine and fir and cedar are all softwoods, and then hardwoods, which are like maple and oak and walnut, are all hardwoods. Cherry's kind of in between. Cherry's not really a hardwood, but it's a little harder than most softwoods, so cherry's kind of in between. Pine is definitely a softwood. And if it's a softer wood, that speaks to its mechanical properties as well. Generally speaking, things like maple and oak and walnut generally are stronger in tension and compression and flexure than softwoods are. All right, here's where we talk about why wood is a natural polymer. So there are a couple of different parts to wood that I want you to know about. The two parts that I really want you to know about are cellulose, and cellulose is the cell wall structure of wood, and these are really long chains of glucose, which glucose is a sugar, and so this is why we say it's a natural polymer. It's also a composite, which it says up here. A composite is a mixture of two or more different things. So the cellulose is a long chain of glucose, and it does form a type of lattice structure, a repeated lattice structure. Then you've got lignin, which is something different. Lignin is kind of like the fiber reinforcement. It's a sticky material. It's hard to break down, and it kind of wraps around the other stuff and reinforces the other stuff. The other stuff being cellulose, and then we also have hemicellulose. There's less hemicellulose in the material, so I don't care that you know too much about hemicellulose, but it's kind of similar to the cellulose. But what I really want you to know about are the cellulose and the lignin in the natural wood material. So cellulose is a natural polymer. It has covalent bonds. It's a bunch of glucose sugar molecules that are bonded together. And cellulose is actually from a mechanical properties standpoint is really what gives it most of its strength and rigidity. And it's reinforced by the lignin. So the lignin is really important also, but its stiffness and rigidity is given by the cellulose. One more thing I want to say is that if you've ever heard anything about like bioethanol or cellulosic ethanol. Have you heard of cellulosic ethanol? That's when you break down the biomass material and then you ferment it with yeast to make ethanol. That's how ethanol is made. You can also make it from like corn. That's the more common way, but cellulosic ethanol is a big research area. And when you ferment the biomass material, what you're fermenting is the cellulose, because the cellulose is the glucose, the sugar that the yeast can consume and make alcohol. Part of the reason I know a little bit about this is because this is what I do in my basement. I brew beer in my basement, and so I know a little bit about fermentation and how yeast works. So yeast consumes sugar, and the sugar in the biomass material is the cellulose. The lignin is the real problem with cellulosic material because lignin cannot be broken down. The yeast cannot consume the lignin, and the lignin is what kind of holds the cellulose together. So you really want to kind of unwrap that material so that the yeast can access the cellulose, but it's difficult. The lignin is the fiber reinforcement that's kind of tying the stuff together, tying the long cellulose building blocks together. So these are the two most important parts. The cellulose is the structural component of the cell wall, and it's about 50% of the mass of most types of biomass material. Lignin is the long and fibrous and sticky kind of fiber that holds the cellulose pieces together, and it gives strength. I mean, the rigidity is given by the cellulose, but think about like one piece of cellulose individually would not be very strong, but if I took a whole bunch of pieces of cellulose and wrapped them all together with lignin, that's kind of what lignin does. Now this thing is much stronger, and it'll be much more difficult for me to break this if it's all wrapped together with lignin. That's kind of how it works with biomass materials. All right, so it's a natural composite. It's a combination of several different materials. You've also got obviously some water and some minerals and stuff, but mostly it's cellulose and lignin. So a few more things about wood. The individual lattice structures, which are that's the cellulose, they're not held real tightly together. And so if you press on it with a sharp pencil or something, from experience, you can make an indentation. So it's not real hard. It tends to be softer than ceramics or metals. And those polymer chains, the glucose that are held together with the lignin, they can flex, but they can't really slide past each other. And so that makes them not really very ductile. If you pull on it, you're not going to get necking like this. You won't see a wood deform like this. So that's why they tend to be brittle and not ductile. The lignin makes it so that the cellulose is not going to melt, but it will burn, kind of like a thermoset polymer material. The cellulose is really just a simple sugar, and therefore it will decay and rot. So that's primarily what decays and rots over time. If a tree falls in the forest, that's what's decaying and rotting. There's also no sea of electrons, so that's what makes wood a good insulator, because there's no free electrons that move around to conduct electricity. And its properties tends not to be very hard, not very ductile. It's not very heat resistant because it can burn at a fairly low temperature. Corrosion resistance, I took some liberties here to define corrosion resistance as its ability to, say, stand out in the elements in the weather over time. So, no, wood is not going to corrode, but it will rot. And so, rotting for wood is kind of analogous to a metal corroding. So I'm going to say that the corrosion resistance, or the ability for it to stand out in the elements for a long period of time, fairly low for most woods. And like we said, it has very low electrical conductivity. The last one is composites. And we say that composites are two or more materials combined together, usually to get the desirable mechanical properties. That's why you're combining these together. And oftentimes, not always, but oftentimes, a composite has kind of a base material and then it has a reinforcement inside there. The reinforcement could be like rebar. Rebar is actually a pretty intuitive example. So we can say that the concrete, and like I said before, concrete itself is a composite material because it has the cement and then also rocks and sand and water. But that is reinforced with the rebar. Usually, most types of concrete are going to have rebar inside them if they're a structural type of concrete for a structural application. So that's what I mean. Like the base material could be the concrete and the reinforcement is the rebar. Rebar is metal. And the concrete is itself a composite, but the cement inside that concrete is a ceramic material. And then you've got, so that's a ceramic matrix. Then, and the matrix means the base material. So you've got other kinds like a metal matrix. In this cutting blade here, you might have a cobalt base material, and then the tungsten carbide is built in there. So the cobalt is the metal, and then the tungsten carbide, if you recall, was a ceramic. So we have the ceramic kind of embedded into the cobalt base material. And then polymer matrices are another type. So the polymer is the base material. And then oftentimes you add reinforcement to that to make it a composite. This is really common for like Kevlar and fiberglass and carbon fiber. What the base material is a plastic, and then you've got the fiber, the Kevlar fiber or the fiberglass fiber or the carbon fiber, which is the fiber reinforcement inside there. And we'll do actually some testing on that, this type of thing in lab 4, where I've got a bunch of different types of plastic dog bones. And one of the ones that we will test in lab 4 has some fiber reinforcement inside here, which makes it a composite, not a pure polymer, and we'll see how that impacts the mechanical properties. So it's two or more materials, usually from different categories. So examples are fiberglass, you've got polyester, which is the polymer, and then the glass fiber, which is the reinforcement. Carbon fiber is epoxy, is a type of polymer, and then the carbon fiber is the reinforcement. Concrete itself is a composite, where cement is the ceramic, and then you've got gravel and sand. And plywood, so the wood sheets are from the category of wood, and then the glue is a type of polymer. So this is considered a composite. Particle board, which is probably what my desk here is made out of. It's got a thin veneer on it, but underneath I'm sure it's particle board. Which is basically sawdust or wood chips that are pressed together and bonded together with glue, which again is a polymer. So generally with composites, what you're doing is you're trying to combine materials to get the best mechanical properties that you can, while also trying to minimize cost or maximize the way it appears, make it appear the best, or maximizing toughness, or maximizing strength. So trying to get the best combination of properties. But there are trade-offs. One of them is that fabrication can be difficult. If wood is very easy to build stuff with. You take a big chunk of wood, you take it to the circular saw or the bandsaw, and you cut it down to size. That's easy. But a composite, well, if you're going to make a piece of fiberglass, I've done this. I used to build, I've built a few boats in my garage. And so usually you build boats out of fiberglass. And the way you do that is you lay down the fiberglass cloth. It's like fibers. It's like a mat. And then you apply the polyester polymer or the epoxy, whatever base polymer you're going to have, and you spread that over it, and then you let it cure. But that's a fairly time-consuming and relatively costly process. Then sometimes you vacuum bag it to get the excess polymer resin out of it, because that's just extra weight. So all of that tends to be fairly time-consuming and kind of expensive for fabrication. And there's a huge range for mechanical properties for composites, because we might be talking about structurally reinforced concrete, or we might be talking about fiberglass. There's a huge range in between there. So they tend to be at least moderately hard. Most of them tend to have sort of medium ductility. They tend to be pretty heat resistant most of the time. They tend to have pretty good corrosion resistance, and most of them are not electrically conductive. So those are some general properties, but it depends. And I do make a few notes down here. So these are generally speaking for most composite materials, but not wood-based. So this does not represent things like plywood or particle board, because those tend to have properties more similar to wood, which we already talked about. All right, so this is a review. We're almost done here. So a review, this is mostly from last time. So let's say we have a solid material that has ionic bonds that's held together with ionic bonds, or a material that's held together by covalent bonds. And let's, for these purposes, assume that that material is in a lattice structure. Then think of a material held together with metallic bonds. And lastly, think of a material primarily held together with van der Waals forces or intermolecular bonds. So for our purposes now, think of this last one as like a hydrocarbon, or maybe a polymer type of material with really long chains that are characterized by intermolecular forces. So for each one of these, think about whether these materials are hard, are they ductile, are they heat tolerant, and are they conductive? All right, so ionic materials, are they hard? Yes, they tend to be pretty hard. Are they ductile? No, they're not ductile. Are they heat tolerant? Yeah, they tend to be pretty heat tolerant. Are they good conductors? No, because they have the electrons bound up in those bonds. Covalent, if it's in a lattice structure, we've said this, that it tends to have the exact same properties as ionic materials if it is in a lattice structure. So is it hard? Yes. Ductile? No. Heat tolerant? Yes. Pretty heat tolerant. Conductor? No. Tends not to be a conductor. Metallic bonded materials, so metals. Are they hard? Moderately so. Are they ductile? Moderately ductile. Yeah. Are they heat tolerant? Kind of moderately heat tolerant as well for some of the same reasons. Are they good conductors? Yes, definitely. Are van der Waals bonds, materials that are characterized by intermolecular forces, are they hard? No. Are they ductile? Yes. Are they heat tolerant? Generally, no. Generally, no. Are they good conductors? No. All right, let's see how we did. Ionic bonded materials and covalent bonded materials, if they're in lattice structures, they are hard. They are not ductile. They are heat tolerant, and they're not good conductors. Metals, are they hard? Medium. Ductility, yeah, I think I said moderately so. So yeah, moderate to yes, because those sea of electrons allows slippage planes to occur. Heat tolerant, medium, because the strength of the bonds are medium strong. Conductor, yes, definitely. And our intermolecular bonded materials are not hard, they are ductile, not very heat tolerant, and they're not conductive. Okay, last little exercise here for practice. You've got these different types of engineering materials. Tell me what type of chemical bonding they have primarily in their material. All right, for iron and tungsten carbide, and polyethylene, and plywood, and pine. All right, so we've talked about most of these. There are a few here where we may have not talked about them specifically. So for iron, that one's pretty easy. It's a metal, so it's got metallic bonding, right? Tungsten carbide. Well, we know that's a ceramic material. And so what type of bonding does it use? Well, it's going to use covalent bonding. Polyethylene, what type of bonding? Well, it has covalent bonds holding the molecules together, but then it has intermolecular holding the molecules together. So two different kinds. Plywood is going to use primarily covalent bonded material, and pine is also characterized by covalent bonds. All right, so this is these are the answers. Iron, characterized by metallic bonding. Tungsten carbide. We said it's a ceramic, but we probably didn't really talk about this, but it is covalent bonding. And polyethylene has covalent and van der Waals or intermolecular forces. Plywood and pine are both held together primarily with covalent bonds. But remember, the covalent bonds, okay, so the cellulose and the lignin, now they're held together with covalent bonds. But remember, you've also got the cellulose chains, and then mechanically, you've got the lignin that's kind of wrapped around here. So the lignin is wrapped around the cellulose material, but not actually bonded to the cellulose material. All right, so that is the end of this presentation, and it's going to wrap up the part of this course on materials science. The reason I like to spend a couple of weeks in the first part of this course on materials science is because it's going to help us understand what's going on later on when we start doing materials testing on these things. You know, by understanding that metals are made up with metallic bonds, and they have lattice structures, and they have grain boundaries, and by understanding how plastic polymers are put together, and how wood is put together, that's going to help us understand what's going on and why they're behaving the way they do when we start to pull them apart and compress them together and bend them and break them in different ways. So it's going to give us some context and understanding of why they're going to behave the way they do when we do testing on them in the remainder of this class. All right, that's going to wrap up this video. In the next video, I'm going to do lab 2. So I'll see you in the next video.